Hello, linear algebra student. This video is for chapter 1.4, the matrix equation. So we are actually continuing with vectors discussion. We say that if we want to have a linear combination of vectors, say for example, instead of using v1, v2, we're going to call our vector a1, a2, an now. The n of them, they are of n entries. So, and then we want to do a linear combination of x1 times a1. That means for a1, I'm going to length it by x1, it's a scalar, and x2 is a scalar, length it by a2, and I add them together to produce a new vector y, say for example. So this expression is called a linear combination of these vectors, just like what we talk about in 1.3. But you can see that to say y, it would be very lengthy, right? We would have to say x1 times a1, blah, blah, blah. So we got to use something that is shorter to describe this expression. And the one tools that we use is matrix, because matrix is a array of numbers. So what happened is we define something called a matrix product. Now, this matrix product is not any two matrix. It's always A times X. What is X? X is a vertical columns of not the original vectors or column vectors that we're talking about. These are weights of all of these column vectors. So they would have different entries. So my A would have 1, 2, 3 up to M. Okay. They would have M entries, but these are n numbers. So they could be different. I could have 3 vectors here, and I will have I would have to have 3 weights, but my entry could be 2 length, the size could be 2, it could be 3, it could be 4. So I would write all the column vector vertically and to fill up a matrix called A. So each A1 is not a number, it is actually a column vectors. And then this representation AX actually is the representation of this. So just define this as a shorthand. Okay, if you see AX, you know that it is a shorthand of writing x1 times a1, x2 times a2. You're doing a linear combination of vectors. And obviously, because each A vectors are of M entries, so this matrix will have M row, and we call it M times N. It has M row, and it would have N column because you have N of these vectors, right? So this is just a definition of AX. So for example, if you see a multiplication like this, a vector, a matrix A, and then a column vectors X, then you can just say that, oh, this actually just means a linear combination of column vectors. So that means 4 times of 3, 4, which is the first vector, and then 1 times of the second vector, 1, negative 2, and then 2 times of the third column vector, 6, 3, right? So this is just scalar multiplication. You can do 12, 16. We talked about this in the last video by the definition. That's what it means. So 12, 6. And then we are adding vector together. We just add corresponding entry together. So 12 plus 1 plus 12 is 25. 16 minus 2 is 14. 14 plus 6 is 20. So the linear combination of this become this, but you can see that how space economic it is to write it this way rather than this long list. So that is actually what it means by matrix product. At this moment, all matrix product has to be A and then a column. Okay, later on in chapter 3, I guess, we will talk about a more general matrix product where the second entry doesn't have to be a column. It could be another matrix, but that would be later. So here we have a linear combination of vectors. Rewrite it using shorthand. So we want, and also make sure that A has to come first and X is following it. So rewrite all the column vector 1, 5, and then rewrite the weights x1, x2, x3. So 2 row, but for the matrix A, but 3 rows for the weights. Okay, and then this is a linear combination of 3 vectors of entry 4. So my column AA would be just copy 4, -1, 4, -1, 0, 1, 3, 0, -5, 3, and then multiply by the 3 entries. So x1, x2, x3. Of course, you can have 3, 3, but I just want to show you in this situation that you can have um, a row that's less than the weights and the root of A is more than the weight also. So it can be any combination because you can combine vectors any way you form. So this is rewriting it back. If someone gives you a AX, write it back as a linear combination, kind of like example 1 that we did. So this is the way. So we say X1 times the first column, 3, 4, 2. And then X2 times the second column, 1, -2, 1. So you can actually do them. So it's 3x1 plus 1x2, right? And then 4x1 plus -2x2. Also 2x1 plus x2. So this is the new vector. Okay, so this is just easier. It's just like a easier way of writing linear combination. Okay, so another theorem that we're going to talk about is how equation. Okay, so we see linear combination actually will result in something, right? If I have linear combination of x1a1 plus x2a2 plus xn equal to a vector b, that would means that I'm solving an equation of ax equal to b. So these two are equivalent. So the writing is equivalent. So if I see an equation ax equal to b, it's the same as a linear combination of x1 of a1 plus x2 a2 all the way equal to b. And in 1.3, we know how to solve this, right? We know how to solve linear combination using systems of equation. So now we have 3 things that are equivalent. So this is the same as this. This one is the same as the systems of equation of you have to write it out. You go to something, right? You go to B1, B2, B3, all those. And so these 3 are actually all equal to each other. You can say matrix equation is the same as linear combination equation is the same as systems of equation. So I have an example here. If I see a system of equation, remember we can write it as a vector equation, right? You can write it as, okay, x1 times a vector of 1, -2, -5. That is all what we learned in 1.3, right? If you don't know what it is, look at 1.3 again. And it's the same as having a vector of 2, 5, 6. So no, 250, right? 250 because there's no x2. So basically, look at all those coefficients as a column vector, and then x3 would be 6, and then this one has no x3, so it's 0, 6, and it's supposed to equal to this new vector 1, 13, 11. So it is a vector combination. So you're asking what combination of these? How can I combine these to become 1, 13, 11? And you can solve this by using augmented matrix, right? So that's what we talk about in 1.3. Now, with matrix equation definition, that would mean 1, -2, -5, 250, 601 times our weights are x1, x2, x3, right? Because these are the weights, is equal to 1, 13, 11. So all these 3 are exactly the same. So they're equal. They are the same thing. And if they're the same thing, that means the way to solve them, to solve this unknown. So in this case, x1, x2, x3 is an unknown. In this case, the weight is the unknown. And in the third case, this matrix also is the weight is the unknown. So it is the same as solving a linear combination, right? So to solve a matrix equation, AX equal to B is the same as solving the linear combination of columns of A. Okay, and to solve this, in 1.3, we use augmented matrix. So if someone gives you a AX equal to B equation, you would use augmented matrix to solve. So solution of AX equal to B. Solution of AX equal to B is if B is a linear combination of columns of A. Use every one of them as a column matrix, and then try to see how I can do linear combination to do it. And to use, how do we solve? And last time we can use augmented matrix. We can use the reduced row echelon form and look at the answer. So here I have A defined like this, B an example, B defined as this. I'm going to solve an equation of AX equal to B. Equation means I need to solve X. So what is X? Solve means what is X, right? And so what is X means I have to determine if it has solution. So determine if it is solution, I would need to look at the augmented matrix. Augmented matrix of A would equal to, so just write them, remember, 4, -6, -7, and also 4, 1, 2. So the last column is the B column. And I want to change into RREF to see if it is consistent, right? So I have did I have it written down? 1, -4, 3. Here, I have it written as C. 1, -4, -3, 3. Oh, it changes. 3, 2, -2, 3, 2, -2, 4, -6, -7, and then 4, 1, 2. 4, 1, 2. So it is in C. I type it in C. So I'm just going to do the RREF of C. And do I have solution? So I have to write it down. So write down the answer. It is equal to 1, 0, 13 over 7. Oh, it's kind of hard to write. 13 over 7, 0, 0, 1, 5 over 7, 0. So we have two prefix columns. So there's 0, 0, 0, 1. But the problem is this is an augmented matrix. The last column is 0, 1 means inconsistent. So no solution, right? Although I have some prefix column, so I might have some free variable, but if this is 0, 0, 0, that is no solution. Right? If it is 0, 0, 0, 0, then I have free variable, but it is not, so this is no solution. So that you cannot do any combination to get this. So this equation AX equal to B has no solution. So now we introduce what is AX and what is a matrix equation, and we now know how to check if AX equal to B has no solution. Basically, just do reduce row echelon form. So do one more, and then we'll look at another aspects of this. U is this. A is 1, -2, 1, 5. 1, -2. Is it 1? It's being blocked. Yeah. 1, -2, 1, 5, 1, -3 is U in the plane spanned by this. So this is actually the same as AX equal to B equal to U has solution, right? If it is spanned by these columns, then you can solve X, right? So this becomes a equation. So it's the same as asking this if you're talking about column spanned by something. So what you do is you would just do this 1, -2, 1, 5, 1, -3, 9, 4, 5, and then do a row echelon form to see if it has solution. Did I have it done? 1, -2. Okay, I have 9, 4, 5. So it's F. So let's do row echelon of F. It become, yes, it is 0, 0, so yes. So the row